Hello and welcome to Amulya's Academy YouTube channel. In this algorithm video series, we are discussing binary search algorithm. And today, let's talk about time and space complexity of binary search algorithm. As I said previously, we can implement binary search algorithm using iterative approach as well as recursive approach. So today, first let's talk about time and space complexity of binary search algorithm written using iterative approach. Okay, so first time complexity. We want to find the time and space complexity of binary search algorithm, not the whole program. That's why we'll analyze only this function. Here first line is function header. Function name is binary search. Parameters are numbers and target. Here this operation doesn't depend on the input size, so it will take constant time. Then the next line low equal to 0. Simple assignment operation, so constant time. Next line, simple assignment operation, as well as we'll calculate the length of the numbers using length function, len function. Simple operation, so constant time. Next here we can see a loop. We'll take this as one block while loop. And here the time complexity of binary search algorithm depends on this loop and its body. And we can calculate best case scenario as well as worst case scenario. Here best case is when the target element is our middle element. For example, if our target is 4, then here low is less than or equal to high. So we'll calculate middle, we'll get 3. Then we'll check whether number of mid is equal to target. True, this condition becomes true. It will return mid and done. So this loop will execute only once. So that is constant time, and here this statement doesn't execute in the best case scenario. It is a simple operation. We are returning a value, so it will take constant time. Now if we calculate the time complexity, here we can see. So in the best case, time complexity is big O of 1, constant time. Now let's talk about the worst case. The worst case is when target is not found scenario. So let's take target as 90. This is our list now. These are index. So target is 90. Here in binary search algorithm, binary search repeatedly divides the search space by 2. We start with a list of size n. What we need to calculate here is how many times we can divide n, that is the size of the input, the list, by 2 until we are left with only one element. So we need to calculate how many steps we need to reach search space with only one element. Why until search space becomes 1? Because when only one element is left, either that is our target element, or we can confirm that target doesn't exist in the list. Here we have an example. Initially low equal to 0, high equal to 7. So we'll calculate mid. So first it will check this condition. This condition is false. So it will check this condition. 40 is less than 90. True. Low becomes 4. Now what is our search space? That is 4 elements left. Low is this. High is this. So 4 elements left in the search space. This is our search space. That is actually half of our input size. Input size is 8. In the first iteration, we'll get search space as 4. Half of the input size. Then next iteration, low equal to 4, high equal to 7. We'll calculate this. Then we'll find the middle element. Then we'll check the conditions. This condition becomes true. So low becomes 6. Now this is our search area. How many elements are present in the search area? That is 2. What is that? It is actually 1/4 of the input size. Right? 8 divided by 4 will get 2. Next, third iteration, low equal to 6, high equal to 7. So we'll calculate this. Now this is our search space. How many element left in the search area? 1. That is actually 1/8 of the input size. Now only one element is present. Either that element is our target element or our target element is not present in the list. Right? So what we need to calculate here is how many steps we need to reach until search space becomes 1. Here we need 3 steps when input size is 8. And we can write like this also. So in the first iteration we'll get n by 2, 2 power 1. Then here we can write it as n divided by 2 power 2, n divided by 2 power 3. We can generalize like this. So when input size is n, if it takes k steps to reach search space as 1, then we can write it like this: n divided by 2 power k equal to 1. Then n equal to 2 power k, if I apply log here, k equal to log 2 n. So if I enter n as 8, here n is the input size, we'll get how many steps? K equal to 3, that is 3 steps to reach 1. So this is how we can calculate this time complexity here. So it will take big O of log 2n. This is a simple operation. It will return value big O of 1. Calculate the time complexity. So time complexity of binary search algorithm is big O of log 2n. Here we need to calculate how many steps we need to reach search space as 1, and here k represents the number of steps, iteration or recursive calls needed until the search space becomes size 1. Okay, next let's talk about the space complexity. Here the first line, parameters, these are the inputs to this binary search algorithm. So constant space, low and high, 2 variables, constant space, and here also mid, constant space. And here we are not using any data structure or recursion, so this algorithm takes constant space. So space complexity of binary search algorithm is constant space. Okay, so next let's talk about binary search algorithm written using recursion. First let's talk about time complexity. Here the first line, numbers target low high. This operation doesn't depend on the input size, so constant time. So comparison operation, simple operation, constant time. Calculating the middle index, simple operations, constant time. Comparison operation, constant time. Returning the value, constant time. Comparison, constant time. And here you can see recursion. So what we need to calculate here is how many steps this algorithm needs to reach search space as 1. We already calculated that we need 3 steps when input size is 8. So we need log 2n steps to reach 1, search space as 1. Here you can see steps when target is 90. We are talking about worst case scenario. Here in binary search, we'll divide the list into half in each step. So to reach the search space as 1, we need 3 steps here when n value is 8. So generally we can take it as log 2 of n. In worst case scenario, time complexity is log 2 of n. In best case scenario, this condition becomes true. So it will execute only once. So time complexity is big O of 1. Next, let's talk about space complexity. Here numbers, target, low, high are the inputs to this algorithm. And middle element, a simple variable, constant space. Next here we can see recursion. Each recursive calls adds a new frame to the call stack. This means recursion typically uses extra memory proportional to the depth of the recursion. If this is our call stack, it will add new frame for every call, and every frame takes big O of 1 time. So here when target is 90, that is worst case scenario, we'll add frames one after the another. Initially when low equal to 0, high equal to 7, mid becomes 3, 40 is less than 90, this condition becomes true. So it will call binary search. When this function is called, this frame is added to the call stack like this. Then next, low equal to 4, high equal to 7. So this frame is added to the call stack when this function is called. And here also same. How many recursive call we need to reach 1? That is 3. But if we have k steps, then we can write it like this. So log 2 of n. So here space complexity is also log 2 of n when we use recursive approach to write the program. Okay, so this is about time and space complexity of binary search algorithm. So that's it for now guys. Thank you for watching. Don't forget to subscribe to my channel. I will meet you in next class. Till then, take care.